Okay, so an actual binomial, the formula for the binomial series, again, this is on table 1. Let me just write it up here and talk about it just a little bit. All right, so that's, it says the binomial raised to a power, its binomial series name, is n equals 0 to infinity. And then that's that k choose n notation times it is x to the n. So it's fairly simple in that regard there. That k choose n, that's where it gets a little complicated. Now in that table they do write out a few terms because let's don't lose sight, because that's where we're going next. Is sometimes it's beneficial to actually write this series out, and that's where they kind of, I guess you will, define out the this k choose n. You know, it's technically we defined it to be k minus 1, so on and so forth until k minus n plus 1 over n factorial. But what it really means is I'm evaluating it term by term. And so the first, if n equals 0, we've got k choose 0. So the first term would be k choose 0 times x to the first. And then the second term would be k choose 1 times x to 0. Since I'm using n equals 0. Then the second term would be k choose 1, x to the 1, and then k choose 2, x squared. So what they did in the book there on table 1 is they went ahead, they evaluated this. So in the book they say this equals k choose 0 is 1, x to 0 is 1. So the first term, just of that's 1. And then the second term, well, if I do k choose 1, it would just be 1 over 1 factorial times x. And then this would be k choose 2, so I'd go 2 times 1 over 2 factorial x squared. Let's see if they can. Oh, yeah, sorry, my bad. Start that over. So k choose 1 is just the first term, so it'd be k. We don't know what k is at this point. So yeah, they just say that's kx because 1 factorial is 1. And then k over 2, k choose 2 would be k times k minus 1 over n is in this case 2, so it'd be over 2 factorial x squared. So that's kind of where they give you the definition of k choose n, but they're writing out term by terms. They give you the x cubed one too. Anyway, here's what we're going to do. We're just going to use this and then simplify this k choose n. Because yeah, if we change something about this, then it's probably not going to look quite like that. But it does have its. It is good to point out that this does give you a polynomial series, a power series. All right. So anyway. And again, yeah, let's go ahead. Let's go ahead and prove this. Because I think it is kind of beneficial, because we proved on that table, we've proven a couple of them. We're not going to prove all of them. You may have to do some of them in the homework, but let me just show you that this is a Maclaurin series. If nothing else, just to review Maclaurin series. All right, so on a Maclaurin series, what we do is we take our function, right, and go with some derivatives. So that's our function. What's the derivative of that? Well, that's just a number. And so it's just a power rule. Bring down the power, and then subtract 1 from the new power to get the new power. Right? Okay. All right, and so double prime, the second derivative. Well, we bring down the power, so it'd be k times k minus 1 up front here. Times then the new power would be k minus 2. Yep. And then the third power, well, we bring down that old power, so it'd be k times k minus 1 times k minus 2. And then the new power is 1 plus x to the k minus 3. So I think we can see the pattern there. Now, it's a Maclaurin series, and so what do we do with that? We evaluate those at x equals 0, right? If it's a Maclaurin series, it's always at x equals 0. So we do f of 0. So the x is 0, so that's just 1 to the k. Well, 1 to any power is 1. For the first term, it's just 1. All right, so f prime of 0. Well, we'd have k times 1 to the k minus 1. Well, it's 1 to any power. This is going to be k. Second derivative at 0 would be k times k minus 1. And then third power at 0 would be k times k minus 1 times k minus 2. Because again, at 0, the x is 0. So it's just 1 to a power. Yeah, and so you can see here, what I've got is the nth derivative at 0. All right, so so I've got k, and then k times k minus 1, then k times k minus 1 times k minus 2. So it's not a factorial there. It's this partial factorial, and it turns out that, yeah, this, your nth factorial, you're going to go down to k times k minus 1 times k minus 2. And then the last term, what do I need for the last, if it's the nth one? Well, it's k minus, and then this number, well, it's 1 less, right? The last, the last number that I subtract from k is 1 less than the n, because this is n equals 3, right? And it's k minus 2. So if I'm doing the nth one, then I need to say it's k minus n minus 1, right? See what I'm saying there? Which is k minus n plus 1. That's what the nth derivative here. Now, in a Maclaurin series then, so by our Maclaurin series, remember it's, you do the nth derivative at 0 divided by n factorial times x to the n. Well, the nth derivative at 0 here is this. K times k minus 1 times k minus 2 times dot 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 k minus n plus 1 over n factorial times x to the n. Well, that's what we're calling k choose n. Ta-da. So it is Maclaurin series. So you can see why they probably like to write it that way, because it's a lot easier to write out. Yeah, it comes from this Maclaurin series formula. All right, but let's see how it works. See how all of it works. So yeah, that one thing to note on the table, which I will provide the table on the test. On the table, it doesn't have this, so that might be something to write down there. All right, so let's see how this is going. All right, so let's write 1 plus x to the negative 2 as power series. Well, on the surface, it's pretty easy. All right, so we got 1 plus x to the negative 2. Perfect match for the formula, except k is negative 2, so I would turn that into n equals 0 to infinity. The k is negative 2, so I do negative 2, choose n, x to the n. But what we have in mind here is, what does that give you? And so, let's write this out and see how we can simplify it, if you will. All right, so negative 2, choose n. We start at negative 2 on top, and then subtract 1, so it'll be negative 2, then negative 3, and then negative 4, all the way into what? K minus n plus 1 would be negative 2 minus n plus 1. So our stopping place would be n minus 1. Wait, yeah, I'm sorry. It's k minus n plus 1, so it's negative 2 minus n plus 1, so it's negative n minus 1. All right? Over n factorial. And so that's where we do our things there. So I pull off the negative 1 to the nth, which would leave me 2 times 3 times 4, blah, 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 until I get to. So I pull off a negative 1 of that, that's just n plus 1, isn't it? Okay, well, pretty good answer. We could put that in. However, this is what I was alluding to here earlier. There's a little more simplifying there, isn't there? Because n factorial is 1 times 2 times 3. All the way up to n. This goes up to n plus 1, so the term right in front of that would be n, wouldn't it? Whole lots are going to cancel. 2, 3, 4 n is going to cancel with the 2. This is just going to leave me what? Negative 1 to the n times n plus 1. They won't all simplify that nicely, but some do. Now, again, be sure it works. Because if I do n equals 0, you know, keep in mind it's negative 2, choose 0, that should always be 1. That's okay, isn't it? It works okay. N equals 1, does it work for that? So n equals 1, yeah, we'd have 2 over 1, which is 2. That's going to work, isn't it? So it works for all of them. That's going to work for all of them. All right, so what we're saying is then this can be replaced by that. I mean, if we didn't simplify it, it'd be that, but this can replace that. So this becomes the power series is n equals 0 to infinity. So negative 2 choose n is just negative 1 to the n times n plus 1 and then times x to the n. And it works for all of them, so you don't have to worry about it. All right. So that's a fairly straightforward one. Hopefully you get the gist of it. Any question? Well, let's try this one. Let's write 1 over square root of 2 plus x as a power source. And so 1 over square root of 2 plus x is not quite in the proper form yet for a binomial series. Binomial series, we need 1 plus x to a power. Well, that's not quite what we've got. Well, the first step here, to make it going in the right direction, let's say, is let's write 2 plus x, sort of bring it up, I guess you might say, to the top. What would the power of 2 plus x be then? Negative 1/2, yeah. Because it's a square root, but it's in the denominator, and so that makes it the negative 1/2 power. Now, for this formula to apply, I don't quite have what's needed yet here either. What's wrong with this picture? It's got a 2, not a 1. That needs to match. This needs to be wrong. So, let's factor off a 2 there, off of this. And so again, you know, it's usually not how we factor. I mean, usually we would not factor that, but because of the formula, we need to factor that. So if I factor off a 2 there, that makes it a 1. What does it make this?
X over 2.
Yeah, dividing by 2, so it makes it x over 2. All right. So now we're in pretty good shape. It's just that now we have this 2 to the negative 1/2, or 1 over the square root of 2, if you want to write that way, times 1 plus x over 2 to the negative 1/2. Now, this is our binomial series format. We've got the 1. We can handle an x not quite matching up. We've done that before. So we're in good shape with that. So this binomial series would be this 2 to the negative 1/2. So I just split up this 2 to the negative 1/2 and that to the negative 1/2. That's all I did there. So that'd be 2 to the negative 1/2. Now this can be written as the power series. N equals 0 to infinity. K choose in. So here K is negative 1/2. So it'd be negative 1/2 choose in. Times, well, if it's this, it's x to the n. If this is x over 2, then that would be x over 2 to the n, right? So we just replace our x by x over 2. So far, so good? All right. Well, let's interpret that, I guess you might say, or simplify that. Negative 1/2 choose in. Well, again, what it means is we start at the k, so negative 1/2, and then keep subtracting 1, so that'd be negative 1/2 minus 1, which would be minus 2 over 2, which would be minus 3 over 2. Minus another 1, which would be minus another 2 over 2, would be minus 5/2. Minus another 2 over 2 would be minus 7/2, until we get all the way to k minus n plus 1, which in this case would be minus 1/2 minus n plus 1, which is minus n plus a half over n factorial. That's what that means. So what are we going to do here? To the top.
Factor the negative 1 to the n.
Factor the negative 1 to the n out. There's negative 1 n times there. We're going to call it that. And then also, with the fractions, what they usually do is factor off that fraction. So let's factor off a half to the n. And that'll leave me just positive term, whoops, on top here, be positive terms, 1, 3, 5, 7. All the way until we get to, now what would this be if I did all that? Well, if I factor off a negative 1, it makes that positive n minus a half. But then, I've also factored off a 1/2, where is it? Right here. I factored a 1/2 all that, so if I divide that by 1/2, what does that make this? 2n minus 1. Good? Good, all right. Over n factorial. Yeah, so this one you won't have any cancellation of the n factorial because n factorial goes one term at a time, 1, 2, 3, so forth and so on. These are just the odd ones, so they usually don't worry about canceling those. However, we need to make sure before I use this to replace that it works for, especially n equals 0. Because at n equals 0, this should be 1. So does it work for n equals 0? Do I get 1? That'd be 1, that'd be 1. Uh-oh.
-1.
That'd be -1, wouldn't it? So it does not work for n equals 0. I think we're okay at n equals 1. and anything greater. But it doesn't work for n equals 0. So I'm going to have to make that adjustment. And we've talked about maybe at least one time before. We talked about that. If it doesn't work for n equals 0, you just have to do that term separately. Okay? So I'll have 2 to the negative 1/2 times, and so this I'm going to replace by this except for n equals 0. So I'm going to do the n equals 0 term here, plus then the rest, so it'll be n equals 1 to infinity. So this can be replaced by this. Yeah, I'm not going to have room for that one. Let's go up here. All right, so I have 2 to the negative 1/2 times, and the n equals 0 term, I'll do that separately. Plus then our series, n equals 1 to infinity. And then this will replace this. So it'll be -1 to the n times 1/2 to the n times 1, 3, 5, 7, the odd ones, to get to 2n minus 1. Oops. Still have them. Over n factorial. What else do I have? X over 2 to the n. Now what about the n equals 0 term? Well, if n equals 0, go back to this. I would have -1/2 choose 0, which is 1, times x over 2 to the 0, which is 1. So the first term is just 1. So that's a pretty good answer. Let's just do, I think, by judging by what the answer in my notes is, here's what they'll do. All right, so we still have this out here, and so usually what they'll do is they'll distribute that. Let's put that here, and then really just kind of put it in front of here. So it'll make out to be, and usually they'll write it not with the negative power. So that would just be, that first term would just be 1 over square root of 2, right? And then that 1 over square root of 2 then will be in front of this. So that's how, judging by my notes here, they typically would want the answer here. Oh, I do see. Now one thing we can do over here with this and this term, let's do this. That's 1/2 to the n, or 1 over 2 to the n. And that's x to the n over 2 to the n. So they may, here's what they may do with that. Couldn't I write that kind of more condensed as x to the n over 2 to the n plus 1? Wait, yeah, 2 to the n, and then another 2.
That'd be 2.
2 to the 2n. Yeah, 2 to the 2. I don't know if they do that or not. Come to think. Yeah, in my notes I didn't quite do that, but just be aware, could happen. Yeah, because that's 2 to the n, 2. So you got 2 to the n times 2 to the n, which is 2 to the 2 n plus n. Or 4, we could say it's 4 to the n. Could say that's 4 to the n. So, you know, sometimes you have to make those adjustments to match their answer. Would I count that wrong if you just left it as is like that? No. Just showing you these, FYI. Good stuff.